Well, welcome to the Calc 1 CBE 6 review. I'm Caroline.
I'm Carter.
Hi.
And I am just a recitation leader for another class, but I like Calc 1.
This meeting will be recorded, so and posted. That no faces will be shown.
Just voices.
So try and avoid saying names.
You can say ours.
We can say ours. We won't say yours.
They
So.
probably not heard me.
Okay. I'll start.
Okay, cool.
Okay. So this one we're doing area under curve, definite integrals, and fundamental theorem of calculus. Okay, so let's do area under a curve first. Okay, so area under a curve, like the whole premise of doing integrals is this type of Riemann sum under like the line. So that's what these two equations are. We can take different types of Riemann sums. So we have the ones that start on the left, and so we can do it from this left endpoint, and then we have ones that we do the same thing, but like we start it from the right endpoint. If I have it, I'm just going to draw another one. If we have the right endpoint here. So these are the little formulas that we use to do that. This one, we start it at n because we don't take into account 0. So because we're starting at the right and we're going all the way up to our farthest point, but this n-1 has to do with that when we get to our very end spot here, because we're at the left endpoint, we're not actually, this is the left endpoint one, we're not actually at the very end of this. So we need to go to n-1 instead. Does that make sense?
Mm-hmm. Yeah.
Okay, so now we can take these rectangles that we're creating under a curve, and we can make them smaller and smaller and smaller and smaller until we have infinitely many. So that's what this limit is doing. It's as the number of rectangles we have under this curve goes to infinity. That's that's kind of how we do integrals. That's the whole premise of integrals. Okay, so this is what I just said. This is how we do integrals. So we have our, this is supposed to be b minus a.
Oops.
No worries. Okay, so we have this b minus a over n that has to do with how much we're changing every time we move to the next rectangle.
Because n is the number of rectangles,
Mm-hmm.
and then b minus a is the distance between the end and the beginning.
Yes, exactly. Okay, and then this, do you know what this x of I is?
I don't. It looks like it goes into the function in the Riemann sum.
So we start here at the a, at our leftmost point, and then this is how much we're changing per if we say we're going, say there's 10 rectangles and we only want to go to the 5th one. This is this has to do with counting all of them up to make sure we're counting all of them up.
So the I delta x is how many of those intervals we're using.
Yeah, exactly.
And then a is where we start.
Yep. Perfect. You already got it down. Okay. And we've already kind of talked about this. Well, actually, I haven't talked about this. So if we have a function that is completely positive, so it doesn't go negative at all, then that's going to be a completely positive answer. But if we have one that it's completely in the negative, the negative and the positive cancel out because we're measuring the distance from our line to the x-axis. Okay.
So
if it's a completely positive function, we've got our area will be positive. If it's completely negative, our area will be negative, which is kind of not intuitive because how do you have negative area?
Right.
But it's the same with negative numbers. What's a negative number?
Theoretical.
Yeah. Okay. Let's move on. Okay. So
question real quick.
Yeah.
So the taking a definite integral already includes the process of adding and subtracting adding together the positive areas and the negative areas, correct?
Yes. So say we start at like, say our bounds, I guess, like our whole entire area was like -2 to 2. The -2 gets, because we're plugging this straight into our function here, that gets taken care of with the negative area. And then we're summing up those areas. So like it shows up in the negative in terms of in here, but because we're summing up all of the individual rectangles, that gets taken care of.
So I was mostly asking if when we take a definite integral, not a Riemann sum,
Okay.
because in the next slide it talks about how if it's partially negative and partially positive, then it's some of it is negative area and some of it is positive area. So in a definite integral, it takes into account, it adds all of those negative rectangles and the positive rectangles.
Yes. Okay, sorry, I understand what you're saying now. But yes.
Awesome.
Okay. Here are a couple of the properties. Like if we start and end at the same spot, it's going to be 0. Because like, what?
Fair enough.
Yeah. Okay, and then if we just flip so if we're going from A to B, we just flip them. That's just like going the opposite direction. So it's just negative of whatever the integral is. And then we can just pull constants straight out because they're not affected by the operation of the integrals at all. So we can just factor them out. And then the integral distributes over multiplication and subtraction.
Addition and subtraction, not multiplication.
Oh yeah, sorry. Addition and subtraction. And then we can split up our integrals if we have like an intermediate point like in the middle. That's what this last one is doing.
Yeah, I remember talking about that. I haven't quite seen its use or used it and stuff yet, but I do remember talking about that.
A great use for that one, you don't usually use it a ton when you're doing continuous functions.
Yeah.
But if you're doing piecewise functions, that one's super helpful. Okay, let's move on. Okay, let's do the first problem. Okay, find the right endpoint definition of the following infinite integral. Okay, wait, I'm going to write it over here. And then inside, I have f of x of I. Am I missing anything?
Times the delta x.
Oh yeah, delta x. Okay, so let's find what each of these things equal. Okay, so we first know that the f of x is already given straight in this integral. So that one's pretty easy. Okay, so now delta x. So the equation was b minus a over n. So we have our b and our a right over here. So I'm going to do 5 minus 2, and then we aren't given a specific n, so I'm just going to leave it as n. Okay, so I'm going to get 3 over n. Okay, and now my x of I, this, if I'm remembering right, a plus I delta x. Okay, so this one, a was 2 plus I, and then delta x, 3 over 2.
And
3 over n. Good job. Okay.
Just sure I'm paying attention.
Okay, cool. Now I'm just going to plug those like straight into the summation over there. Okay, so I have the limit as n goes to infinity of the sum of as I goes from 1 to n, and then my f of x, I'm going to have 2, and I have my x of I, so I'm going to put this in here, plus squared, and then times 3 over n.
Isn't a cube just a square?
It is. I don't know what's going on, but okay. Okay, so I'm just going to simplify this more. The inside of this, if I just quickly write this again. Okay, basically all I really want to do is just simplify the 2 and the 3 over n. I don't really want to expand the other part out. I'm going to have 6 over n times 2. Okay, and that's it. because we just needed to put it into the formula. And that's
Riemann sum?
And that's that Riemann sum. It is the same. I just kind of wrote over it. Oh, and also, this is wrong. This should be n. It doesn't. This on the top of the summation there was
it
a.
has that
Yeah.
infinity, but it's supposed to be an n.
Yeah. Okay. Okay, you want to do it?
Yeah, I'll do it. Yeah, so I guess for that problem one, the questions I looked at the CBE, it looks like it's a multiple choice. This is true the best one. I would recommend writing it out on paper and then matching it, because otherwise, like there'll be a cube instead of a squared, which is easy and to like mess up on, and then you miss a point right there.
Which you can't afford to miss many.
No, yeah. So this one, yeah, this is also one that's like it's like this type true or T or F or true or false. So it's asking us, is the integral equal to the area above the x-axis and below the curve on the interval 0 to 4? So it's pretty much asking us, suppose we have like the curve that looks like this, is the integral equal to that curve? This will only be the case if this function actually is above the curve everywhere. If it dips below, then in the interval, and we're integrating from, now this is a bad picture, but from there to there, then we're gonna get this area minus this area plus this area. That is not the area above the x-axis and below the curve, because
It's not solely
there's
that area.
yeah, there's more area. So really, to answer this question, I want to see, is the function go negative in this interval? If it does, then it's false, because we're going to be in this case. If it's always positive or at most 0, then we're nowhere in this case. So now how we're going to answer this is saying, is 3x squared minus 12x plus 8 always greater than or equal to 0 on the interval 0 to 4? So I don't know, that minus 12x right away is giving me like the, hey, maybe not, but I'm thinking we should like do it more rigorous instead of saying probably not, because that's not a great answer.
Guessing is not great.
Yeah, guessing is not a great, when you need to get 90%. So let's try and find zeros, because zeros are pretty easy. So when does this equal 0? 3x squared minus 12x plus 8. And does this equal 0? Well, that's the quadratic formula. So we get negative b plus or minus the square root of b squared minus 4ac, so times 3 times 8 all over 2a. So these, yes, I want to put, where's the erase? No.
Spoilers.
Yes, I need,
And just cross it out.
I'll just cross it out. It's 3. So simplify this, that's 12 minus. Plus or minus, yes.
Sorry.
Now you get up here and you start writing, and then you're suddenly like, oh, and then you make the mistakes that are silly. Yeah. 4 times 3 is 12, times 8 is 96, minus 96 all over 6. I suspect we could have just factored this, but oh well. 144 minus 96 is, I'm gonna actually, I don't know. Top of
48.
Oh, 48. Maybe we couldn't have all over 6, so that's 48 is 4 times 12, or 16 times 3.
6.928
So
is the square root of 48.
okay, so we have 12. I mostly just want, I guess, I don't want to use janky calculator on the CBE, so I'm going to do this as much by hand as I can, because I don't enjoy that little pop-up box.
That's fair enough.
Yeah, 48 is 4 times 12, so 16 times 3, that comes out to a perfect square, so if that's 4 square root of 3 over 6. So we get 2 plus or minus 2 thirds square root 3. Both of those, now we're going to be stuck in the issue of, is this in the interval? Because what I want to do is create a number line of the function and say, hey, here is 2 minus 2 over square root 3, and here is 2 plus 2 third square root 3, and then say, based on this number line, where is the function positive, where is it negative, and where is it positive? And then we'll be able to look at the interval 0 to 4 on this number line and see if where they line up. So, for example, these are roots. I don't know exactly where it is. I know that as the function gets very big, this 3x squared term is going to dominate. So it's going to be the function is going to be positive and positive infinity, and then also positive and negative infinity, which is the square term. And then in between then, I know these roots have multiplicity 1, which is odd, so they're going to switch sign, it'll be negative there. And so I also know this interval is centered at 2. So 2 is in the middle right there. That's in the interval 0 to 4. So there's a negative value in the middle of the interval 0 to 4. So the function we are in this case, because here is like 2. The x value, that's bad 2. Here's the x value 2, and the function's negative there. So now we said, hey, our function's negative in the middle, so this is false.
So one way that somebody suggested me to do it was to plug in the two bounds into the equation to see if they go positive or negative.
That would work. That's like if either of them is negative, then we would know for sure. So in this one, we plug in 0, we're going to get 8. We plug in 4, and we're going to get, I think we're also going to get 8.
So it wouldn't.
That wouldn't work.
Misleading.
Sometimes that'll work. I've seen it with cosines and sines, and I think that's a little bit easier to tell than this because it gives you like pies. And
Yeah.
I know pi 6 way better than I know like 4 square root 3 over 2. And,
Yeah.
you know, so I think the ones
Best to find the zeros.
Yeah, but I like finding the zeros and then plotting a number line because when the multiplicities are odd, it's really easy to build a number line. Just plug in like a million in your head and see the x squared term dominates, and then just
You say multiplicities are odd. What do you mean?
the multiplicities of the roots. So when we factor this equation, this equals x minus, I'm running out of space, but this term, this
Yeah.
2 minus 2 third square root 3, and then
x.
times this x
Yeah.
plus, no, minus again. This is where the plus is 2 over 3 square root 3. So this 3x squared minus 2x plus 8, those are the two roots, and they both have exponent 1. So their multiplicity, this is what the multiplicity is. It's 1, it's odd. It's the exponent. That means on the number line, it crosses the x-axis there. Like right here, as x is less than negative 2, or 2 minus 2 thirds square root 3, we're positive, and greater than is negative.
Interesting.
And we know that just from the multiplicity being 1, which is odd.
Okay then.
So you can use that on the first derivative test too. You can just draw a number line and do that really quickly as opposed to taking second derivatives and using it. Though most people prefer the second derivative test, but it's a neat little trick to just plug in very large numbers and then just quickly fill out a number line based on factoring it.
Awesome.
So that's my favorite way to solve this.
I like that one.
Cool.
Okay, I'll do the next one. Okay, the graph of the equation y equals f of x is shown. Alright, so we're just gonna find the areas of all of like the shapes in here, I guess. Okay, so let's like separate it. So I'm gonna do, so this one will be a square, and then this one's gonna be negative, so I'm going to do these separately. Okay, then one big triangle, and then the negative one over here. And these two negative ones will be the same. Okay, so the area of this one. So we've got 2.
Can't see what you're. Okay. But you can't see what you're pointing at.
Sorry, yeah, I guess so. Okay, of the square, 2. It's like 2 by 2 square. So it's gonna be negative 4.
Yeah.
But both of these are negative. Oh wait.
That's not right.
Just the height's negative.
Yes, you're right. Okay, so we're just gonna go negative 4. Okay, then let's do this one. This one is 1 by 2. So that's gonna be 2, but then it's just gonna be negative 1 in this area. And this one's also gonna be negative 1.
Because each square is only a half.
Yeah.
I was like, there's 16 squares in that.
Yeah. Okay, cool. Now we need to do this
The big
the
triangle.
big triangle. So I gotta stop saying this. Okay. So this one is the base is 4, and then the height is 4. So in total, it's 16. Then we gotta half that, so it's 8. Okay. So we've got the integral from -5 to 3. Okay, we've got 8 minus 2 minus 4. So 2. Easy enough. All right. Do you want to talk about this one?
Yeah, I'll talk about
Okay.
this one. So this is fundamental theorem of calculus. It's a little late in the course to be talking about it, but it's very, very useful.
Very fundamental.
Very fundamental. And we can actually prove it using calculus as opposed to some other theorems. So the first part is the integration is the opposite of differentiation, which is very nice because that means we have inverse functions. Kind of. And so if we have a continuous function f, which most of the ones we deal with in the class are, then, and x is a point in the interval a to b, then what we can do is if we have a function that's the integral of this little f, like big F is the integral from a to x of little f dt, where t is just a dummy variable. But then when we take the derivative of this, we do, differentiation is the inverse of integration, so we're just left with little f of x. We take, if there was something else, like if it was x in the denominator, then to be f of x, if we, t dt, if this, I don't know, call it capital G of x to distinguish it, and then we took g prime of x, it would be very similar, only now it would be negative f of x because of this
integration.
Yeah, because when we integrate, if we did actually solve this integral directly, then it would be like f of x minus f of a. This is f of x minus f of a by the second part, which we haven't talked about yet in this. And then we take the derivative of that, and it goes back to f prime of x. So that's why this negative shows up. And then furthermore, we can just expand on this to say if we're integrating from a to any function of x, then let's call it little g, not to be confused with my big G. Then when we take the derivative of that, we do chain rule. And we would say, because this, to go, g is the second fundamental part, this would be f of g of x minus f of a. And then when we take the derivative of that, we do the chain rule. The antiderivative of capital F is lowercase f by definition. And then the g of x stays inside and multiplied by the derivative of the inside, which is g prime of x. So it makes for problems that we wouldn't want to actually do the integration and then do the differentiation. We can just go straight to this final answer and not have to actually integrate it and then differentiate it, because that'd be a lot of work. So, for example, in this problem, in this course, we don't know how to integrate e to the t squared dt. It is possible. It's like a whole page and a half.
That's very fun.
Luckily, we don't need to do it. We can just go straight to taking the derivative. So I guess I'm going to use the notation from the last one and say that g of x then is x squared plus x, and then our answer, f prime of x, is going to be f of g of x times g prime of x, where I guess I should identify what f of x is. F of x is that what we're integrating, e to the x squared, which I guess maybe the eraser doesn't want to show up. Maybe that should be f of t, but it doesn't matter if it's x or t in there when it's written separate. So then we can just plug this straight in, because this line is our final answer. So f of g of x is e to the g of x squared, so x squared plus x all squared, times the derivative of g, so times 2x plus 1.
So when solving when solving for these definite integrals with a variable in the integral, you substitute in the variable portion for t in essence.
Yeah, we're
whatever.
essentially, so I guess I will overwrite this with the very bolded t. What we're doing, we're plugging g of x in for t. So everywhere we'd see t, we would put x squared plus x. So,
And then taking the
and then
derivative.
taking the
of-
derivative of g. So I guess
And
I can write this on the side too. 2x plus 1 and then just multiply it. So it is essentially like chain rule, which we've done for a few months now, at least 1 month. So hopefully we feel comfortable taking,
And then it's
chains.
the same with just a single x, except that the derivative of just a single x
Yeah.
is 1.
So
it
if,
disappears.
yeah, it just disappears because the derivative of x is 1, and who bothers writing all the times 1s at the end, because there could be as many of them as you want.
Yep.
And then if we check our answer, it is what we have.
Yay.
So I like these problems because all of this work is kind of, it's useful for explaining it, but when you're doing the CBE, you can kind of go straight to plugging it in to the exponent and then just taking the derivative, like plugging it into the function and multiplying by the derivative. You don't need to show a bunch of this work unless you're showing someone else your work.
Yeah. Or making sure that you did it
Yeah.
right.
So I guess it is useful to write down that way, you have a sanity check when you're doing it.
Yeah. Cool. Okay, so now we're doing the second part of the fundamental theorem. So we're, if we have a continuous function, like, and with like a closed bound, so a to b, we can just do the main. So this is like the derivative of f of x, the big f of x. So we can just do the original top bound minus the original bottom bound. Does that make sense?
So with this integration, yes, which means that the integral of that would be the antiderivative of capital F,
Mm-hmm.
which we can write out as capital F of B minus capital F of A.
Yes. And we're going to do a couple examples of this one, I think.
Okay.
Yeah.
Okay. Determine the value of the following integral. Okay, let's see. So, could we use this fundamental theorem on this question? Let f be a continuous function. I mean, I guess that, okay, sorry. That was a little bit confusing. This is like kind of, when we take the integral of something, when we take the integral of this, we are already getting back to my big f of x.
Yes.
And then we're just evaluating it at the endpoints.
Yes.
Okay. Okay, so I'm going to take the integral of this inside part first. Okay, -4 to 3, 2x to the third plus 4x. Okay. The integral of the inside part. Okay, so I'm going to raise the power. So I've got x to the fourth and then divide by that power. So I've got 1/2 x to the fourth plus, and then this one, raised by the power, I've got x squared, divide by it, I've got 2. And then we're going to evaluate it from -4 to 3. Okay, this is going to be a little nasty, I think. Okay, let's see. So we've got, this is our first part, and then minus, oh dang, -4 to the fourth.
It's 256.
Oh, okay,
I have a calculator.
excellent. And do you get a little calculator on the CBE?
It's
Oh,
just
that's
a
so
standard.
nice.
It's just a standard add, minus,
Oh, cool.
multiply, divide.
That's super
So
nice.
Just 4 times 4 times 4 times 4.
And that was 256?
Yep.
Okay. Okay, and then we've got 2, and this is 16. Cool. Okay, now this first one. Do you know what 3 to the 4th is? It's like
81.
81, yeah. Okay, plus 2 times 9. Okay, now we've got to subtract this all. Okay. 256 divided by 2 is 128.
Yep.
Oh, nice. I was like 80% sure of that one. Okay. Okay. I don't think 1/2 over 81 over 2 isn't gonna be nice.
It's 40.5.
That plus 8 at the end. Should it be plus 32?
It's plus 32.
Oh. Yep. Perfect. Thank you. Okay. So I'm gonna add the 18 and the 32 and the 120. Oh wait, I'm gonna subtract. Okay, so 32 minus 18 is like 12. This tells you how good I am
It's 14.
at brain math. Okay. So 14. Okay, 14 minus 128. That's 114.
Mm-hmm.
Okay. And I think it simplifies that down even more. I don't. Do you need to on the
No,
CBE?
you can, as soon as you have numbers, you could, that second line, you could type that in if you really wanted to.
Oh, really?
Yeah.
Okay. Well, let's see what the fraction. I think it gives us, the fraction form.
Because 114 times 2 is 228.
81 minus 228,
Yep.
negative 203. All right, cool. I didn't know that you could just plug that in on the
Yeah.
CBE.
So if you're like us and you struggle at the mental math.
Yeah.
Well, first off, you have a paper there and a calculator.
Yeah.
But I would get to I don't know, maybe like this one or this one and just type that in, because I'm gonna mess up typing in a big long line, but I'm also gonna mess up on the math. So
Yeah.
pick your poison.
So true.
114. So 81 minus 228 is negative 147, not 2.
I think
Oh, then I did something wrong somewhere.
I think it was going from this line to this line.
Oh.
Like 128 plus 32 is 170. 18 minus 170 is
Not 114.
Yeah, not 114.
Okay.
It's like 152 or something.
Well, thanks.
But
That's perfect.
that's why I would say probably type in this line.
That's why they encourage you just to not simplify.
Yeah. In later classes, it's more simplification, but in this one, it's just about, do you know how to do calculus? And the algebra is just going to be something that you struggle with throughout the entire course, and throughout the rest of math even. But
So true.
yeah. So now, I guess another problem of the very similar sort. We're asked to evaluate this, and I'm going to rewrite it so that I have space to the right of it. So we have 3x squared over the square root of x dx. Now, off the top of my head, I can't think of an antiderivative or something that has this as a derivative, but we can rewrite this in a way that's easier to do. Like, we have an x to the squared and a square root of x in the denominator. We can write those both as x to powers. So we have the integral from 0 to 4 of 3x squared divided by x to the 1/2 and dx. And now this is something I am more familiar with because it's powers. And I know, hey, from my algebra courses, we can combine these exponents to be 3x to the 3/2 dx. And this, I know how to do this. This is like a power rule. So oftentimes you'll be given an integral that you're like, I don't know how to do this, but then after like splitting up a fraction maybe or combining terms, you'll say, I know how to integrate that. So this, just like we said, you raise the power by 1, so 3/2 plus 1 is 5/2, and then divided by that new power. The 3 sticks around for the ride, and we evaluate from 0 to 4. We can simplify it up a little bit. So that's 6 fifths x to the 5 halves evaluated from 0 to 4. And that turns into 6 fifths of 4 to the 5 halves minus 0. And we can factor out that 6 fifths from both times and subtract them separately, or we could multiply the 6 fifths times 0. It doesn't matter. In this case, it especially doesn't matter because it's 0, but in generally, if this wasn't 0, it still wouldn't matter. So 4 to the 5 halves is 2 to the 5th, which is 32. So we have 6 over 5 times 32. And I'm not going to go much farther than that. The answer is 192 over 5, which is what you would get if you multiplied 32 and 6 together. You get the 192. So
Nice.
yeah, you have to remember, like, sometimes simplify what they give you at first, because it starts hard to deal with, and you can make it a lot easier. I don't want to do an inverse question rule.
All right, let's do the next one. Okay, I think there's one more of these, and then we move on to other things. But this one's with cosines and sines. Trigonometry. Okay, cool. So let's first take the integral of both cosine and sine. Actually, what I think would be good is if we used the linearity property of integrals and split it up. So we've got cosine of 2x dx plus 2 sine of x dx. Okay, so what is the integral of cosine of 2x?
Sine of 2x times 2.
Sine of 2x times 2. How'd you get that?
Because the antiderivative of cosine of x is sine of x.
Okay.
And then because the x is a function of itself,
A function in and of itself, it's 2 times x. We have to take the derivative of the inside.
Okay.
Multiply to it, which gives us 2.
Okay, cool. So let's check it by quickly now taking the derivative of it. Okay, take the derivative of this. We're going to get cosine of 2x. And then we need to take the derivative of the inside times 2. So we're going to get 4 cosine 2x. So we're like almost there, but it's not quite what we want. The sine of 2x part is perfect.
We divide by... Oh, yeah, we have to...
I found the eraser.
We
Yeah.
have to divide by the derivative of the inside.
Yes, perfect. So we want, because we want that 2, the 2 doesn't appear, like the derivative of the inside doesn't appear. I can like make it appear, but I also am like making it not appear by multiplying by 1/2. So like this part disappears. Okay, so I'm gonna get 1/2 sine of 2x. The switching between the, like, is it 1/2, is it 2? I always struggle with that. That part is so hard. Okay, and then for the second one, there's no inside function, which is nice. So I'm gonna do 2, and then the derivative of, the integral of sine is negative cosine. So this is going, I'm so glad I found the eraser. This is going to become, oh no. Okay, sorry. This is going to become a negative. Okay, and now I need to evaluate this on my bounds. Pi halves to pi. Okay, so let's do the first one. 1/2 sine of 2 pi, that's just gonna be 0. Okay, minus 2 cosine pi.
That is 2. Well, minus 2.
Minus 2, and then we've got that negative in the front, so it's just gonna be positive 2. Okay, 2, and then this one. Okay, so now we've got 1/2 sine of, now this one's just pi, so it's gonna be 0 again.
that first space, it would be a -2, right?
This one?
Yeah,
So when we have,
because we're not minusing yet. The function itself, it has, that sine plus cosine.
oh, are you talking about this minus? Or this one? The first one or the second one?
I mean, it's the same minus, right?
Yeah, you're right. Okay, so we'll go back to this part. So the integral of sine is going to be negative cosine. So that's where this negative comes from. Okay, and then cosine of 0 is 1, and then cosine of pi is going to be -1.
Right.
So then we have cosine, so like
That's
this is
why
a
it becomes
-1, and this was a -2 out here, so it just turns into just regular 2.
Yeah.
Cool. Okay, now and then we have 2 cosine of pi halves, and that's also going to be 0. So now we've got 2 minus, so this is just 2.
Do we minus? Yes.
Cool. Any questions?
No.
Okay. Do you want me to talk about this one?
I can talk about it.
Okay, sure.
We did a long beginning, a long spiel. So, of course, we can't apply integrals. They're useful. So one thing they're useful about is finding the average value over a function. If the integral is the total area under the curve, then if we divide by the length of the interval or multiply by 1 over the length of the interval, then we're going to get the average area under the curve, or like the average value of the function. It's like, you could think of it as if we had like a function that looked like a large pile of sand, and then we smoothed it out, it would look something like this. That'd be the same as if we like added up all the sand and then split it up evenly over the interval. So we can use that to determine the average value of a function, and you could apply this in real life too, to like finding the average speed of a car. But here it's just not a function, so we're going to do more calculus. So to find the average value of the function, we're going to use that formula. So I'll write it up top. It's 1 over b minus a times integral from a to b of f of x dx. So in this case, our a is 0 and our b is 2. So we can put that in immediately. The integral from 0 to 2. And our f of x is given. So it's 4x cubed plus 3 plus e to the x dx. And then now we just need to evaluate the integral and multiply by this 1/2 out in front, and we'll be done. So we have 1/2. The antiderivative of x cubed is x to the 4th. And then we're going to divide by the new power, and we get 4 over 4, or just 1. This plus 3 becomes a 3x, and the antiderivative of e to the x is e to the x. And then we need to evaluate that from 0 to 2. So we have left with 1/2. I'm going to big parentheses there. So we have 2 to the 4th plus 3 times 2 plus e squared minus 0 plus 3 times 0 plus e to the 0. And so you could type this in to your answer if you wanted to, but I don't like typing in like unnecessary stuff, so we can simplify it a little bit. So we have 1/2. 2 to the 4th is 2, 4, 8, 16. 16 plus 6 plus e squared, and then this whole second half always becomes a -1, because that's e to the 0. So we're left with 1/2 times 16 plus 6 is 32, minus 1 is 31, plus, you're right, 21. I went straight to 32 because it's doubling, but e squared. So our answer is 1/2 times 21 plus e squared. And that is what they got. So
Yay.
the math works out.
I love it when the math works.
Mhm.
Okay, cool. I think we're gonna do another one of this one. Okay. Determine the area that lies beneath the curve. That. and then over the x-axis on the interval -1 to 3. Cool. So let's use that same formula.
So this isn't the average.
This is, I don't think this is average.
Yeah, this is not, they're not asking for the average.
Oh, it's not. We could
They're
find the
asking just for
average.
integral.
We won't find the average then. All right, then let's just,
I mean, we'll have to find the integral
so,
In finding the average.
Yeah.
So, I mean,
okay. So I guess there was only one average question. Okay. I guess this probably is just setting it up and then we'll solve it. Cool. So this is my function and then these are my bounds, -1 to 3. Cool. So then I'm gonna integrate this. This is going to become raise the power, divide by the power, and then plus x from -1 to 3. Cool. So this is 1/3 times 3 to the 3 is 27. Yep. Okay, and then plus 3. And then minus, we'll do these. And then -1 to the 3 is minus 1/3 minus 1. Okay, so this is, we'll do this part first. 27 plus 3, that's 30. So this is going to be 10. And then minus 1/3 minus, this is going to be,
is that 1/3 supposed to be negative?
yes, it is. Okay, so we've got 9, I've switched the -1 to just fractions. So this is now 9/3. -1/3 minus 9/3. So that's minus -10/3. Okay, cool. And then, so 10 plus 10/3. And you can just leave it like that. But we're going to do
It's 40/3.
40/3. Perfect. Okay, let's see what we got. 40/3. Yay. Okay, cool. And that's the end of the review. So if you need any more help, Tutoring Center is right through that door. And I'm also going to post this video on our YouTube channel. And yeah, do you have any other questions?
Nope. I think I should be okay.
Okay, perfect. Well, good luck on your CBE.